Okay, pre-cal, here we go. Removable discontinuities in graphs. Isn't that fun to say? Removable discontinuity. Go ahead, try it. Okay, so basically what it is, it's just a hole that occurs in a graph. What would this look like, Ms. Griggs? Well, let's say we've got a rational function that looks something like this, and let's say there's a place actually in one part of it where there's a hole. That's what it looks like, okay? Only prettier than that because my drawing's horrible. All right, so it's basically a hole in the graph. It's a value that it jumps over, essentially. So how do we know if there's a hole in the graph? Well, there's a really easy way to tell. After you factor, if you can reduce, there's a hole. That's how you can tell. So what are we going to do? Let's look at our steps. Step number 1, we are going to factor this puppy. I know you're getting, thrilled with that, all the factoring. Okay, so we are going to factor this. Magical times. All right, so once we factor, then the next thing we're going to do is we're going to reduce. And I want you to notice what we're reducing. The x minus 2's are going to cross out. They are going to reduce. So pay attention to what you reduced. X minus 2 is what reduced. So that's going to tell you where there's a hole. So essentially what you do is solve for this. So x equals 2. That means there's a hole at x equals 2. We need to find the y value at x equals 2 because a hole is always an ordered pair. All right? Because a hole is an ordered pair. So we've got one half of the pair, we need the other half. How do we do that? Well, we are going to use our reduced fraction, and we are going to substitute in this 2 in for x into the numerator and the denominator. So 2 plus 4 over 2 plus 5 gives me 6 over 7. So there's a hole at 2 6/7. That is how we do this. It's a magical time. All right, let's do some examples. I know you're excited. All right, number 7. Very first thing we do, we are going to factor this. X and X, 3 and 5, positive and negative. X and X, positive 3, positive 1. Okay, are there any, make a sentence. Are there any holes in this particular situation? No, because there's no reducing going on. So for this particular example, we have no holes. So let's find all of the other stuff. So the asymptotes, vertical asymptotes are going to occur at x equals -3 and x equals -1. The horizontal asymptotes, let's see if there are any of those. The degree in the numerator is equal to the degree in the denominator. That means that my horizontal asymptote is going to be equal to the ratio of the lead coefficients, which is 1/1. All right, since I have a horizontal asymptote, there is not a slant asymptote. There are no holes because we didn't reduce. And of course, your x and y intercepts. I know you're getting just crazy with these. Your x-intercept, you're going to set the numerator equal to 0. So we have x-intercepts at 3 and -5. The reason we're finding our intercepts every time is because we're going to need those when we graph. Okay, my x-intercept is when x is 0. So if you'll notice your original function, these are zeros, so I basically have negative 15 over 3, which is negative 5. So 0, negative 5 is my y-intercept. Magic. Okay, let's look at number 8. Don't panic. This is going to factor as a difference of squares. And down here, we're going to factor by grouping. So in my first group, I've got x cubed plus x squared. So I'm going to factor out the x squared. And then in this grouping, I'm going to factor out a negative 4. Excellent. Now notice that in the denominator now, I'm going to have x squared minus 4 times x plus 1. So that's going to factor again. So my final factored form is going to look like this. There you go, babies. Okay. From that, we are going to look at what we can reduce. We are going to reduce first. The only thing, if I were to write the domain here, this is where it would occur. That is the only thing I do before I reduce. Everything else comes after I reduce. My asymptotes, all of that. My y-intercept, everything. Okay, so these go away. That means there are going to be holes. That's what that should tell you. Notice that the entire notice that the entire numerator is gone. That does not mean 0. It means 1. So my equation from which I will find all of my asymptotes is 1 over x plus 1. So I've got a vertical asymptote at x equals negative 1. I've got a horizontal asymptote at y equals 0 because my degree in my numerator is 1 less than it is in my denominator, or it's less than the degree in my denominator. This means I will not have a slant asymptote, but it does mean there are going to be holes in this graph. I know there's a hole at -2 something and +2 something because that is what reduced in my equation. So I've got to use division, or I'm sorry, I've got to use substitution to figure out what those other values are. So in my reduced form, I'm going to substitute in a -2 here, and that gives me a -1. I'm also going to substitute in a 2. Oops. Jumped ahead of myself there. So 1 over 3. So those are the holes right there. Okay, x-intercept. Well, my x-intercept occurs when I set 0 equal to the numerator. So there is not 1. Because that is not a true statement. 0 does not equal 1. My y-intercept occurs when x is 0. So there is a y-intercept, just like that. All right, moving on. I'm going to try to get through these as quick as possible so you don't grow weary of hearing my voice. Well, who am I kidding? That's already happened. Poor kids. Bless your little buttons. I know I'm a headache to deal with. All right, so this is going to be my reduced form. Notice there's a hole, so be careful. All right, so my reduced version is, oops, if I could write, is x plus 4 over x plus 3. So my vertical asymptote is x equals -3. My horizontal asymptote is y equals 1 because the degree in the numerator is the same as the degree in the denominator. So it's going to be 1 over 1. Slant asymptote. Well, there's not one because I have a horizontal asymptote. Okay, holes. I know there's a hole at 1 something, and now I'm going to use my reduced version and substitute the 1 in for the x. So 5/4. And you will find that a lot of times the y value in the whole is like some weird fraction. So don't freak out about that. All right, x-intercept. Set the numerator equal to 0. So I've got an x-intercept at -4, your y-intercept. The x's are both zeros. So 0 4/3 is my y-intercept. Okay, last problem. I know you're tired. I'm tired. So 2x and x, be careful with your factoring here. But, the nice thing about this though, 5 only has one option. Okay, so 5 here, 1 here, because this is 10 and this is 1. It's going to give me a -9, so this would be negative and positive. Okay, this is already factored for us, but notice that it's x plus 4 squared, which means x plus 4 times x plus 4. Yes, we're going to reduce. There's a hole. Okay, so vertical asymptotes occur at x equals -4, and that's it. We're just going to write that one time. So my reduced version, sorry, I meant to write that. So we'd have it to refer to. Okay, my horizontal asymptote for this one, my numerator degree is less than my denominator degree. So that means I'm going to have a horizontal asymptote at 0. There is no slant asymptote. And holes are occurring at x equals 5. So I'm going to use some substitution to find out what the other value is, the y value. Okay, so I've got 10 plus 1 is 11, and this is 9 times 9, which is 81. I warned you that sometimes the y value is weird. All right, so x-intercept, we're almost done, yay! Set the numerator equal to 0. So -1/2, 0 is your x-intercept. Your y-intercept occurs everywhere x is 0. So I've got 0 plus 1 over 4 times 4, which is 16. So 1 over 16. There's your y-intercept. Awesome. I hope you've enjoyed this lovely purple writing.